It's on.
Okay, hello everyone. Thanks for joining us today. Today we are very glad to host Dhruv Rohatgi. He's a fourth-year PhD student in MIT. His research is at the intersection between computer science, statistics, and machine learning. He's doing incredible work in reinforcement learning, imitation learning, recently also language models. He's advised by Ankur Moitra, and he interned 2 times at Microsoft. And thanks to one of these interns, I think we have the... No, sorry, I was confused, but he will mention briefly one of the work he did in his internship today. But today the main topic is presenting exploration is harder than prediction, cryptographically separating reinforcement learning from supervised learning. I'm really interested to hear more about it. Thanks, Dhruv, for accepting our invitation. The stage is yours.
Thank you, and thanks for the invite. So I just want to start, this is joint work with Noah Golowich and Ankur Moitra. And I want to start by unpacking the title a little bit. So exploration is sort of the fundamental challenge that we think of that makes reinforcement learning special. If you think of some basic reinforcement learning task, where some robot is trying to interact with its environment, maybe it has some downstream goal, like trying to locate the cat in the house. And exploration is sort of important if it wants to be able to solve this goal. Prediction, on the other hand, is what we think of as the basic task in supervised learning. So this encapsulates things like regression and like classification, where the learner is seeing some labeled data, for example, an image and a label of whether the image is a cat or not a cat. And the learner wants to produce some sort of classifier or regressor. In this case, they want to learn how to predict cats. And in this talk, what I want to discuss is comparing these two problems, exploration and prediction, from a computational perspective. And in the first part of the talk, I'll give some motivation for why this is an interesting question. So the basic motivation here is reinforcement learning with large environments. As you probably all know, many of the places where we would like to apply reinforcement learning involve environments which can be naturally modeled as having massive or even infinite context spaces. One example can be in robotics, where the context seen by the robot might naturally be modeled as some very high-dimensional vector consisting of all the sensor data. Another example is in language modeling. We can think of post-training language models as a reinforcement learning task. And here the context space might be the space of all possible prompts and even all possible partial completions of some text. And a third example is in multi-agent RL, where if we have an agent that's trying to learn how to play a game, its context might be the sequence of all actions that have been seen so far. And so here again, the context space is going to be extremely large. So what unites all of these examples is the fact that the classical model in reinforcement learning of a small and unstructured Mark composition process, or MDP, is insufficient. If we try to model an environment as an extremely large MDP, then with no other assumptions, any sort of reinforcement learning task is going to be completely intractable. And as a result, the central challenge when we want to apply reinforcement learning in these sorts of environments is to design natural structural assumptions that nonetheless enable efficient exploration. And this is what we call the field of reinforcement learning with function approximation. So there's been a lot of work on this in the last decade or so. Most of it has been from a statistical perspective. There's a bunch of different model classes, and in a bunch of these cases, we know that there is an efficient algorithm for exploration. And we even now know a fairly sharp characterization of when the statistical complexity is bounded in terms of quantities such as the decision estimation coefficient. So here we have a pretty nice picture. But you might ask, what about the computational complexity? Like, when can we design end-to-end computationally efficient algorithms for reinforcement learning. And here the picture looks quite different. We know that if the MDP is small, then we can do everything efficiently, and there's a couple different algorithms for this. We know that if the MDP is large, but the transitions factor linearly, then again, there's a computationally efficient algorithm based on a variant of least squares value iteration. But for all these other model classes, we have no hope. There is a computational lower bound in all of these model classes. And so here the picture is looking quite grim. It's saying that for these rich model classes, end-to-end computational efficiency is often too much to hope for. But let's dig a little bit deeper into where this came from. It actually comes from the fact that even in supervised learning, most problems are computationally intractable in the standard pack learning formalism. So this includes works showing computational lower bounds for pack learning neural networks and similar results. And there's a sense in which we can rigorously show that reinforcement learning is no easier than supervised learning. And I'll touch back to this later. And so the computational lower bounds from the previous slide are actually just inherited from computational lower bounds for supervised learning. And I would argue that these sorts of computational lower bounds are somewhat deceptive. The reason is that supervised learning has seen massive empirical successes in recent years. Basically, you take a neural network, you do gradient descent, and on natural data, things seem to work better than we would expect from our formalisms. And recent work in reinforcement learning, both in theory and in practice, has tried to exploit this success by building on supervised learning and optimization primitives. So instead of asking the question, when is reinforcement learning computationally easy? I would argue that the better question to ask, or maybe the more useful question to ask, is when is reinforcement learning computationally as easy as supervised learning? And this is the focus of this talk. Now, this is not an entirely new question. So in some sense, the field of Oracle efficient algorithm design in RL is asking the same question. So we say that an RL algorithm is Oracle efficient with respect to some optimization or learning Oracle O if it's computationally efficient and provably correct when given query access to O. In other words, we ask for computational efficiency, but modulo queries to O, and this gives us a lot more flexibility in designing algorithms for rich model classes. So this is, I think, a very useful paradigm for trying to exploit the successes of supervised learning in a principled way. But there is one thing that I would say is missing from this line of work, which is some consensus about which oracles to use. In other words, almost every paper in this line of work is using a different oracle or set of oracles to solve its particular task of interest. As some examples, some of these oracles solve minimization problems, whereas others solve min-max problems. Some of them are used to estimate value functions. Some of them are used to estimate kinematics of the MDP. And some of them are used to learn features for the MDP. And there's a bunch of other design choices that go into the specific design of the oracle that I'm not going to get into. But at the end of the day, it seems like we have an entire zoo of different oracles in theoretical RL, and it's not really clear how to compare them. This might be important in practice because these oracles are going to be implemented by heuristics. And so the reinforcement learning algorithm's performance will fundamentally depend on what oracle it's trying to use. In other words, when we design an algorithm that uses access to a particular computationally hard optimization oracle, we're fundamentally making an assumption. So what we should be asking are, what are the minimal assumptions that we need to make? In other words, what are the minimal oracles that we need for Oracle efficient RL? And this is a sort of complementary way of framing the question from the previous slide. And I'll revisit this perspective at the end of the talk. For now, I'm going to turn back to the sort of pure computational complexity perspective of understanding when is reinforcement learning harder in a computational sense than supervised learning. The reinforcement learning task that I want to discuss is exploration in a fee-decodable block MDP. The supervised learning task is fee-decodable regression. Informally speaking, a fee-decodable block MDP is a model in a natural class where the state space is very large but very structured. The fee-decodable regression task is a generalization of pack learning, and it's also the most basic primitive in reinforcement learning. And in the next part of the talk, I'm going to give some formal definitions for both of these, unless there's any questions. Okay, so the reinforcement learning setting we're going to consider is episodic and finite horizon. So as you probably all know, this means that a sample from an MDP is an episode of interaction between an environment and an agent. The environment will give the agent some context from a context space. The agent will choose some action to play. And then the environment will transition to a new context conditioned on the previous context and previous action. And this will continue some number of time steps. After some number of episodes of interaction, the agent would like to produce some good policy or set of policies, where good can mean a couple different things. For our purposes, we'll be mostly interested in the goal of policies that explore all possible contexts. But you could also talk about reward maximization problems, where you want a policy that achieves good reward in expectation over the episode. So that was the very basic MDP setup. But as I mentioned previously, we need more structure. And in our setting, the structure will come in the form of a block MDP. To motivate block MDPs, if you haven't seen them before, the motivation can be thought of in a simple setting where you have this robot interacting with the environment. And let's consider what the robot sees. If the robot has a camera, it's going to see some very high-dimensional image. It's going to move, and at the next time step, it'll see a different image, and so forth. So the natural context space for the agent will be the space of images, which could be extremely large. But from the perspective of the environment, it could be that all that actually matters is the location of the agent at every time step. And so this naturally defines a latent space of locations, which perhaps we could assume are decodable from the images. And it seems also natural that the size of this location space is much smaller than the size of the image space. And the hope here is that the agent can learn to exploit the latent structure in order to explore more efficiently. And that's what block MDPs are trying to formalize. So as some notation, let's fix a context space X, a latent state space S, and a function class phi, also known as a concept class, that maps from X to S. Now, the phi-decodable block MDP assumption states the following. There is some unknown decoder phi star in the function class phi, such that for any contexts X and X prime and action A, the probability of transitioning from X to X prime, conditioned on playing action A, only depends on A, phi star of X, and phi star of X prime. In other words, the latent state phi star of X contains all relevant information about X, and we believe that it's a much more succinct representation. Now, what makes this computationally and statistically challenging is that the decoding function phi star is unknown a priori. And so learning this decoding function is somehow entangled with the reinforcement learning task. The goal in block MDPs is to learn a policy cover. This is what we call it sort of reward-free exploration in block MDPs. So what we want is a set of policies that visit every latent state with near maximal probability. And here we allow for some small additive error epsilon, as well as some polynomial multiplicative error in the number of latent states, the number of actions, and the horizon. And with this goal, you can show that the sample complexity of exploration in a block MDP scales polynomially with the number of latent states and various other parameters, including log size of the function class. What's crucial here is that there is no dependence on the context space, and so we say that this algorithm is sample efficient. But of course, this theorem says nothing about computational complexity. This is just showing that there's a statistically efficient algorithm. So that's block MDPs. And we want to compare that task of exploration to the following task of phi-decodable regression. So this is a supervised learning task where we're given IID samples. Every sample is a pair x, y, where x is a context living in this context space, capital X, and y is a real value between 0 and 1. And we would like to approximate the conditional expectation of y given x. So this is the function that we would like to estimate. And we make this assumption, similar to in the block MDP setting, that there's some phi star in the function class phi, such that y is independent of x, conditioned on phi star of x. In other words, the expected value of y given x only depends on phi star of x, which we call the latent state. So here again, we can show, and this one is fairly easy, we can show that the sample complexity of this task scales polynomially in the number of latent states and log size of the function class. And you can think of this as essentially a generalization of pack learning for finite concept classes. So here we see that the algorithm is sample efficient because there's no dependence on the number of contexts. But this problem, because it generalizes pack learning, is going to be computationally hard for very expressive function classes such as neural networks. And so rather than...
Sorry, quick question. Like when you talk about this phi-decodable regression versus the previous setting, I thought that in the block MDP, the sort of prediction task what the phi does is that it predicts a finite discrete latent state from the context.
Yes, that's correct.
So why that corresponds to like a regression problem where the label is a continuous real number between 0 and 1?
That is a good question. I'm going to try to motivate that in the next part of the talk.
Okay.
Yeah, and if it's not clear after that, then we can discuss.
Sure, cool. Yep.
So yeah, there's a good question of why did we define the regression problem this way, as opposed to all the million other supervised learning problems we could have defined? So one first observation is that, and I'm going to give some proof sketches for all of these later. One first observation is that it's actually a necessary oracle. So you can prove that if you want oracle efficient RL, your oracle needs to be at least this powerful. The second reason is that it's actually a useful oracle. So maybe this partially answers the question of why we define it this way, is that this oracle enables estimating value functions in block MDPs. And moreover, it actually enables end-to-end RL, or oracle efficient RL, in several special cases of block MDPs. So one of them is reward maximization if we are already given a policy cover. One of them is reward maximization with horizon 1. This actually follows from the previous one. And one of them is exploration in block MDPs if they have deterministic dynamics. So there's a bunch of interesting special cases where it is actually very useful. And it doesn't trivialize the RL problem. Before our work, it was not known whether this oracle was sufficient for oracle efficient RL, because all existing algorithms used more complex oracles. And for these reasons, I'd argue that it's an ideal baseline for trying to understand what makes RL challenging or not challenging. And so next, what I want to do is build some intuition about this regression problem by giving some sketches for most of these results. Does that sort of answer the question, or? Okay, thanks. So background results. First, I want to explain to you why regression is necessary for reinforcement learning. In other words, why there's an efficient reduction from regression to the task of reward maximization in block MDPs. And it turns out that for this reduction, it even holds when the block MDPs have horizon 1. So what are we doing? We would like to solve a regression task. So we're given a bunch of labeled regression samples, and we have access to an oracle that solves reinforcement learning problems. So let's invoke the reinforcement learning oracle. To do this, we need to simulate interaction with some MDP. And we do this using our samples. So for each sample x, y, we simulate an episode of interaction with the oracle. We give it the context x. It plays the action y, which lives between 0 and 1. And we give it some reward. And this reward is going to be larger when the action is close to y. So what we can see here is that if the reinforcement learning oracle solves reward maximization, then it's actually producing a policy that is a good predictor of y given x. And that's exactly what we wanted. So this shows that...
But in this case, you need to have a infinite and continuous action space?
So we discretize the action space, like 0 to 1, based
on
the error that
I see.
Yeah.
Okay.
So you're correct, the action space grows, but yeah, if you want inverse...
There's a 1 over epsilon like growth, but... Yeah.
That's right. Yeah.
I guess it's just like I think overall as like there may be more nuanced questions as to what if like action space is finite and then is constant size, like does that change the story and so on? But yeah.
That's right. Yeah. So here we're sort of thinking about like everything. We're thinking about algorithms that are polynomial in all the parameters, and then this reduction makes sense. So this shows that RL is at least as hard as regression in the way that we defined it. Next, what I want to show is why regression is actually a useful oracle. So the first claim is that we can fit value functions with regression. In other words, for any reward function and any particular step h, we can estimate the value of the q function for any fixed action using regression. And the way we do this is pretty simple. We just draw a bunch of trajectories starting at various contexts x of h. And for every x of h, we label it using the reward obtained by that trajectory. And then we invoke the regression oracle on this data set to compute some q hat function. And we do this for every fixed action. So the reason this works is that the conditional expectation function is exactly the q function. And under the block MDP assumption, the q function only depends on x via phi star of x. So it satisfies the conditional independence assumption that we needed. And as a result of these two facts, we can see that the oracle will return a good approximation of the q function.
And just to clarify here, this is essentially just doing regression onto Monte Carlo targets.
Yes. That's right.
And so it'll be policy specific.
Yes.
Like you'll learn like q pi for some pi.
I should have put a pi here. Yeah. This is a q pi. Yeah. So one way we can use this, or use a very similar idea, is to perform reinforcement learning when we have access to a policy cover. So we can show that if a policy cover is already known, then there's an oracle-efficient algorithm for reward maximization in block MDPs with a regression oracle. And so here the algorithm is, again, something that people are already probably familiar with, which is just fitted Q iteration. So we estimate Q functions starting at the last layer of the MDP and going back to the first layer. And at every step, we use the regression oracle to fit the Q function based on the Q function for the next layer. And we generate data using our policy cover. And then we define our output policy as just the argmax policy for the estimated Q function. So there's a lot of technical details that go into showing that fitted Q iteration works, but this is like a standard classical result, so I'm not going to go through it here. But you can show that this formally works, as long as the regression oracle is accurate. So that sort of was avoiding the exploration task entirely. Next, I want to show that if we have deterministic dynamics, then the regression oracle is sufficient for exploration. So the idea here is that when the MTP has deterministic dynamics, we can, without loss of generality, consider policies that are just fixed action sequences. And then a policy just corresponds to a path in the MDP. And we can run an algorithm called predictive path elimination from prior work, which builds up a policy cover layer by layer. So we start with some policy cover for the first layer. And then for every subsequent layer, we initialize the policy cover by extending the previous policy cover with all possible actions as continuations. So this will multiply this number of policies by a factor of A. But if we had a cover, if we visited all states of the previous layer, and then we sort of try all possible actions at the current layer, this will be a good policy cover. The issue is just that this blows up the policy cover by a size factor of A at every step. So we need a pruning step. We need to deduplicate the policy cover at every step by identifying which pairs of policies lead to the same latent state. And if we can do this deduplication, then we're set. And so the remaining question is, how do we actually deduplicate? And this is where we use the regression oracle. In particular, we can generate contexts from each of the two policies and ask the regression oracle essentially to classify them. In pictures, if we consider two policies which lead to the same latent state at some time step, then if we generate contexts from those two policies at that time step, the regression oracle has no way of distinguishing them because they come from the same distribution. So the regression error will be no better than the error of random guessing. On the other hand,
sorry, here when you say regression error, like what is your regression target?
Yeah, sorry. So the contexts from say the orange policy will be labeled 0. The context from the green policy will be labeled 1.
Oh, okay. So you're essentially using a regression oracle as a classification oracle.
That's right. Yeah.
One question that sort of that stems from that is whenever we're saying regression oracle and so on and so forth, like when you use function approximation, we often talk about what kind of target function you're trying to learn, realizability and all of these, right? So is that something that you will like list ahead of the time, or you say, whenever I run this regression, like whatever it is, like I just give myself realizability of whatever I want to learn?
Are you asking about like the assumption on the input data or about the output data? Or like
I'm asking about the oracle itself. So like, because I guess I'm thinking more about like open the black, like, okay, maybe like open the black box in some sense, like, but it's like, is it an oracle such that if you give it any like input label pairs, like it's always like well specified in some way?
I see. So I guess I'm thinking of it as an oracle that receives samples, and I only require it to work if the samples are IID and well specified in the sense of satisfying the conditional independence.
No. I guess when I say well specification, I'm talking about the function class it uses, which is inside the oracle, which is a part of the black box, but it's something. So okay, so here is how do I put it? So the process you just described, right? That when you see zeros and ones, yeah, maybe you have this maybe we can talk about this other case, right? You have different latent states, and you would expect that your regression oracle will be able to do a perfect classification of it.
Yeah.
Right? Or at least like better than random, right?
That's right. Yeah.
Which means that when I actually implement the oracle, or when I look into the details of the oracle, let's say the oracle is using a neural net or something, that the neural net should be able to actually represent a function that distinguish between these two, the context generated from these two different latent states. And that will be an assumption.
I guess.
And I guess all I'm saying is that, like, okay, tomorrow, let's say you use the oracle for some value function approximation, then that means that you need the realizability of that value function, right? So I'm just saying, like, are you going to list all these realizability assumptions at some point, or you're just saying that whenever I say I have an oracle, I assume that it has whatever realizability it needs for whatever prediction tasks we're interested in?
Yeah, the latter. So like it's
The latter,
parameterized.
okay.
It's parameterized by the function class phi. So like for a particular function class phi, you could say like, let's pretend we have an oracle for regression when it satisfies the
Okay,
phi decodability.
Okay, got it.
Yeah, so this is all I wanted to say about deterministic dynamics. But it gives an interesting example where we can actually do something interesting with the phi decodable regression oracle. And now what I want to mention is what oracle do we currently need for the full task of exploration and block MDPs. So if you're not familiar with it, one oracle that is sufficient for this task is two-context regression, which has the following statement. Instead of being given pairs of samples, we're given triples. Each sample is a triple x1, x2, and y, where x1 and x2 both live in x, the context space, and y is the real number. And here we want to estimate y given x1 and x2. So that's the basic statement. And there's also a decodability assumption or a realizability assumption based on phi, which I'm not going to define formally here. But at a high level, this oracle is useful for estimating kinematics of the MDP in the same way that the previous oracle, the standard regression oracle, was useful for estimating value functions. Yeah.
Yeah, from this definition, I really don't understand the difference between the two-context regression oracle and the oracle. It's just like, I don't care about what x is. It's like, okay, no, we have pairs of x. Like, what is the big deal? How is this any different?
So it's different because the realizability assumption will be different. So like if you think about one context regression and you instantiate it with like half spaces or something, then this one will be something about like intersections of half spaces, like to make it concrete. So it's sort of it's a different function class. Now, I mean, you could ask like, do you care about the difference between one context and two context regression, even like given that distinction? Maybe those are like qualitatively the same to you. And I mean, that's like a philosophical question, but at least like concretely, they are different problems. Like this is sort of one context regression with like phi squared, if that makes sense, as your function class.
There is no phi here. In this definition, I only see a conditional expectation. It's just like a regression function defined as usual, except that you're telling me that the context now has two parts.
Right. So
but
there is an assumption
to phi at all.
Yeah, there is an assumption I didn't write down formally here, which states that we assume that the expected value of y given x1 and x2 only depends on phi star of x1 and phi star of x2. So that's the phi decodability part of this.
Right. Okay.
Just analogous.
And in that case, so I guess this maybe follows up my question on realizability. Is that like you don't need a separate realizability assumption? All you need is that you have this phi class because phi star is in phi.
That's right.
And that phi maps high dimensional x to some low dimensional, like predicted latent states.
That's right.
So essentially, whatever you do after phi, like something tabular, like you can even afford like a tabular prediction after having the correct phi star.
Yeah.
Okay, that makes more sense.
Okay.
Yeah.
So
like-
two-context regression on its own is not like this. It's like in the context of this phi and like.
Yeah, I've sort of defined just like the optimization bare bones question, but you have this phi decodability on top of this.
And the part that makes this oracle, which means that abstracting away like some optimization aspects, is the fact that we're not making any structural assumption on the phi class. So everything about optimization and that is being abstracted away is in the phi class, correct?
That's right. Yeah. So when I'm talking about like oracle efficient RL algorithms, I guess I'm thinking of algorithms that do not care at all about the phi class except through the oracles that they're using.
Okay. Okay.
So yeah, our main results sort of give some clarity about what sorts of oracles we need for block MDPs. So our first result shows that under a cryptographic assumption, there is a concept class phi such that there's a separation between exploration in block MDPs and phi decodable regression. So here the phis are the same. And I'll explain to you which phi we choose later. And there is a caveat here. So this is a somewhat technical point, but in actuality, our construction will be a particular subset of phi decodable block MDPs for a particular phi. And we'll only consider the regression problems that arise from MDPs in this family. But this is sort of a technical point I don't really want to get into unless people are interested in it. Our second result is conceptually has the same message, but is technically incomparable. So we show that under a standard cryptographic assumption, there's a concept class phi such that the task of reward maximization in block MDPs cannot be efficiently reduced to phi decodable regression. So this is incomparable because it's applying to reward maximization, which is an easier task. So in that sense, the theorem is stronger. But it's not proving a computational separation. It's just proving that there is no oracle efficient algorithm.
So for the first one, when you say distribution specific regression, I'm wondering if the point is that you're showing that one thing is harder, like exploration is harder than the regression, but so regression is easier, but it's only easy for the kind of distribution you see in that MDP construction.
That's correct.
But in general, like if it's possible to design other distributions that also makes the regression hard.
Yeah, so when we look at the construction, that may be more clear, but yeah, that is an interesting open question of like, if there is an example where regression is just completely easy in the pack sense, in the like distribution independent sense. So for most of the talk, I'm going to focus just on the first result. And in particular, I'm going to focus on a baby version where we strengthen the RL task to strong exploration. So recall that in standard exploration, we want to learn a policy cover where we're allowing for epsilon additive error and some polynomial multiplicative error. In strong exploration, I allow for epsilon additive error, but no multiplicative error. And this will make our construction task much easier because strong exploration, it can be computationally challenging, even when the horizon is constant. So we can use a much simpler family of block MDPs. So to give some intuition for where our separation comes from, I want to return to the definitions of block MDPs and of phi decodable regression from a graphical perspective. So phi decodable regression says that y and x are independent conditioned on phi star of x. So that gives us sort of a directed graphical model that looks like the following. And in block MDPs, we have this sort of graphical model because the transitions only depend on the phi star of x's, on the latent states. So another way to think of these models is that there is some latent distribution or latent MDP where everything interesting is happening. But we don't directly observe the latent stuff. We observe it through an emission distribution. And so the model can be described as sort of the latent distribution plus the emission distribution. And notice what we observe in these two problems. In the regression problem, we observe x and y, but not phi star of x. And in the block MDP problem, we observe the contexts x of h's, but again, not the latent states. Now, intuitively, it seems important to be able to solve the task of decoding x back to phi star of x. In other words, inverting the emission distribution. This is not a formal statement, but it will guide the intuition for our proof. And so the idea for our main result is to construct an instance where prediction and exploration both have the same goal of decoding x back to phi star of x, but they have different computational complexities because they have access to different information. And this is the key idea. That in the regression task, the learner has access to these responses y, but in the block MDP task, the agent only has access to the contexts. To make good on this idea, I need to give you an instance, so I need to describe the latent instance as well as the emission distribution. And I'm going to start with the latent instance. So what does the latent MDP look like? Well, we're going to pick an MDP with state space that's binary, 0 and 1. The action space is 0 and 1, and the horizon is just 2. And the transitions will be deterministic, and they'll just be defined by mod 2 arithmetic. So if you play action A on initial state S, then you go to S plus A mod 2. So how do we perform strong exploration? Well, if we want the best chance of reaching the state 0 at the second time step, then this requires playing the policy pi of S equals S. So in state S, we need to play action S. And this is trivial if we directly observe the initial state. But in a block MDP with this latent structure, we are not going to directly observe the state. We'll observe some contexts conditioned on the latent state. And so now we have to learn the policy that maps the context X back to the latent state S. So what we've shown here is that in a block MDP with this latent structure, we actually, if we want to perform strong exploration, we actually need to learn how to decode the latent state. And this makes good on the intuition from the previous slide. So next I have to describe the emission distribution associated with the latent structure. And this will be based on the hardness of learning parity with noise. So if you're not familiar with this LPN problem, it looks as follows. Suppose we're given samples where each sample is a pair u comma y, where u is a uniformly random binary vector, and y is a measurement of u. It's an inner product of u with some secret vector sk, plus some Bernoulli noise with bias 1/2 minus delta. And this is all mod 2. And we'd like to learn the secret vector sk, which we can call like the secret key. So this problem, as far as we know, is computationally very challenging. And a popular conjecture in cryptography is that there's no polynomial time algorithm for this problem when the bias is 1/2 minus delta for constant delta. In our case, we actually need a somewhat non-standard variant of this. We're going to make the observation that the time complexity of the best algorithm for this task actually degrades very rapidly as delta decreases. And in particular, we're going to make the conjecture that the time complexity of LPN with noise level 1/2 minus delta scales super polynomially in delta inverse. So this is consistent with everything we know, and I could talk more about why this is a meaningful conjecture if anyone's interested, but we're going to run with it for now. And it suggests the following refined idea for our construction. We will construct an instance where strong exploration is at least as hard as LPN with noise level 1/2 minus delta squared, but regression is at least as easy as LPN with noise level 1/2 minus delta. And if we can do this, then we've proved our separation under this conjecture. So what does the emission distribution look like? I'm going to first describe what it looks like in the context of regression. So there's some unknown vector sk, and the regression samples are pairs x and y. So we generate them by first generating a latent state s. We can assume it's uniform from 0 or 1. And then y is some function, some random function of s. Without loss of generality, because everything is random, let's say that it's s plus some Bernoulli noise with bias epsilon. The important part is the emission distribution. So conditioned on the latent state s, the emission x will look as follows. To unpack this a bit, the first part of this emission is essentially an LPN sample. The only difference is that we've added in the latent state s into the second part of this LPN sample. And the final part of the emission, or of the context x, is an encryption of the latent state. So we can see here that our decoding function phi star is going to be the decryption with the secret key sk. And our function class will just be the set of all possible decryption functions. And what we claim is that with this setup, the regression task actually reduces to LPN with noise level 1/2 minus order delta. So this is intuitively believable because in the context x, there is some noise with bias 1/2 minus delta. And there's just two cases to consider. The first case is that epsilon is close to 1/2. In other words, the response y is basically independent of x. And this means that there's some constant prediction function that suffices for regression. And so we can find it efficiently. The other case is if epsilon is far from 1/2, in which case there is some signal relating y to x. And in this case, it suffices to learn the secret key sk, and we can do this by XORing x with y. And doing this removes the latent state s from our emission, and we just end up with exactly an LPN sample with noise level 1/2 minus some constant times delta. And we can do this to a bunch of different samples, and then we can solve LPN with this noise level to recover sk, which gives us the decryption function that we need. And so that's basically how we solve the regression task using an LPN oracle with this noise level. The harder part is the reinforcement learning side of things. So here, the latent structure is exactly the mod 2 MDP that I described a few slides ago. And the emission distribution is the same as what I described on the previous slide. So we have these LPN samples, and we have these encryption functions. And what I want to prove is that the strong exploration task is as hard as LPN with noise level 1/2 minus delta squared, which I will do by proving a somewhat subtle reduction that you can reduce LPN with noise level 1/2 minus delta squared to the conjunction of two different oracles. First, a strong exploration oracle, and second, an oracle for LPN with the lower noise level 1/2 minus delta. And if I can do this, then I claim that, in fact, strong exploration is as hard as we want. So there's two steps to proving this reduction. First, I need to argue that if I give you an LPN sample with noise level 1/2 minus delta squared, I can simulate an episode of interaction with this block MDP. what makes this a little challenging is that I cannot actually simulate the latent states and then conditionally sample the contexts. This turns out to be impossible. I have to actually simulate the contexts without ever simulating the latent states. And the second step is, once I have learned a strong policy cover, I need to show that it's possible to recover the secret SK. And this will use an oracle for LPN with the lower noise level 1/2 minus delta. So now I'm going to give brief sketches, maybe just for the first one. So the first part was to show that if I'm given an LPN sample with noise level 1/2 minus delta squared, I can simulate an episode of interaction with the block MDP. A failed attempt would be to sample the latent states and then conditionally sample the contexts by adding the latent states into my given LPN samples. And the reason this doesn't work is it has the wrong noise level. So in my block MDP, I want the noise level to be 1/2 minus delta in each context. But the LPN samples that I'm given need to have the noise level 1/2 minus delta squared. So things don't add up. The intuition for making it work is the following. Essentially, what I want to show is that in my trajectory in the block MDP, the amount of information about the secret SK is actually quite small. I want to show that it's essentially as small as the amount of information in the LPN sample that I'm given. And to do this, I observe that the first context x1 by itself is independent of SK because of this latent state S1. Because it's uniformly random, it's sort of masking all of the information about SK. And so what you can think of as happening here is that the stochasticity of the initial latent state makes it much harder for me to learn things about my hidden parameter. Additionally, intuitively, the only way to get information about SK is now by contrasting x1 and x2, because x1 and x2 individually have no information. And how do I contrast two binary vectors? Well, intuitively, I XOR them. And if you look at x1 XOR x2, this actually looks a lot like an LPN sample with noise level 1/2 minus delta squared. So here, this is sort of the key intuition, that the information in my block MDP, in my trajectories from the block MDP, is only, I can only extract this information by contrasting my contexts, because I do not have any labeled responses for my contexts. All I have is these contexts themselves. Now, this was only intuition. You can actually prove a formal reduction where you take the LPN sample and you split it into these two contexts, x1 and x2. But this requires some more technical effort, so I'm not going to go through it. So that proves the simulation. The second part was to show that if I have a strong policy cover, I can learn the secret. And basically, this is using the property of the mod 2 latent MDP. So the mod 2 latent MDP means that a strong policy cover must contain an approximate decoding function. And I can use this decoding function to sort of back out LPN samples from my contexts. And then I can apply an LPN oracle to learn SK. So this proves the hardness of reinforcement learning for my block MDP. And putting everything together, I can prove my baby theorem essentially by contradiction. So I can show that if strong exploration were as easy as regression, then I would be able to show that LPN with noise level 1/2 minus delta squared is as easy as LPN with noise level 1/2 minus delta. And so that completes the proof. I'll just say like one word about the full theorem, where we want to prove a hardness against exploration instead of strong exploration. So here the technical challenge is that we need to go beyond horizon 2 in order for exploration to be computationally challenging. And so we actually generalize the mod 2 latent MDP to what we call a counter MDP, where essentially the counter MDP is asking the agent to make guesses about some random bits, and it will count how many correct guesses have been made by the agent so far. And this is useful because it has a lot of algebraic structure, and it helps us prove simulation results, where we need to simulate the dynamic data, namely the trajectories from a block MDP, using the static data, namely samples from LPN. And this is sort of the key technical challenge in proving these hardness of RL results. So that's all for the technical stuff. I wanted to conclude just by talking about implications, particularly for oracle efficiency. So recall our question about what are the minimal oracles needed for oracle efficient RL. What our results essentially show is that phi-decodable regression is not a minimal oracle, because even though it is necessary, it is not sufficient. And this proves a separation between the task of exploration in block MDPs and some of the easier tasks. So it shows a computational benefit of having deterministic dynamics. But it does raise a question: what is the minimal oracle, if there is one? So here I just want to briefly pitch a recent work of mine with Dylan Foster, where we show that this phi-decodable two-context regression is actually a minimal oracle. It's necessary and sufficient for the task of strong exploration in phi-decodable block MDPs. So just to remind you, this is what two-context regression looked like. And in some sense, modulo the caveat that this only applies to strong exploration, this clarifies the computational landscape for block MDPs. For example, it shows that the min-max representation learning oracle is more complex than necessary in a sort of rigorous computational sense. A couple of technical future directions. There are some senses in which our cryptographic separation is quantitatively weak, although I will remark that these are addressed by our oracle impossibility result, namely the second theorem that I mentioned as our main results. And there are some questions about the minimal oracle result. Namely, it would be interesting if there's an analogous result for standard exploration or for reward maximization. This seems particularly interesting because strong exploration only makes sense as a solution concept for block MDPs, which have only a small number of latent states. So if we want a more general computational taxonomy for reinforcement learning, it seems we need to go to one of these different tasks, one of these more standard tasks. From the conceptual perspective, I want to just discuss a couple things. So if we zoom out a bit, most work in theoretical RL for function approximation has taken what I would call a structure-centric perspective, where we ask what are the weakest structural assumptions that enable sample efficiency or that enable oracle efficiency. And our work is more motivated by a computation-centric or oracle-centric perspective. So we ask questions like, what are the weakest oracles needed in particular model classes? And what can we do with a particular type of oracle? For the first question, our results now give a fairly cohesive understanding for block MDPs, modulo the technical caveats from the previous slide. But they say very little about more general model classes, and I think this is a generally interesting direction. It's not even clear what are the right questions we should be asking here. For the question of what can we do with a particular type of oracle, I want to highlight one very recent work, which shows that max value ensembles can be competed with efficiently using just a regression oracle. And this is an interesting example where weakening the solution concept enables us to do something more computationally efficiently. And I think this is also an interesting direction for future research. Thanks for listening.
Great.
Nice.
Thank you.
Yeah, I guess I have a more high-level question, not that high-level, but so one of your constructions had this essentially only like a one-step or two-step short horizon MDP, right?
That's right.
If I remember correctly, the high-level like idea or the final claim is still that exploration is harder than regression over there, correct?
Yes, for a
How
different
is
notion
a
of exploration.
yeah, but how is exploration hard in a short horizon where like I can just take actions uniformly randomly and basically hit everything?
Yeah, so that's because we don't allow. So that's because we want strong exploration. So we want like max d pi minus epsilon. So you'll incur a factor of 1 over number of actions if you take a uniformly random policy.
Right. But having uniform actions, I would have all the data I need to like say learn things, right? Like for example, as you said before, like if you have the policy cover, you have fit like if you use FitIQ or something like that, you can pretty much like learn anything you want like in this MTP.
You can learn any downstream reward function. That's true.
Right.
But that actually does not let you solve strong exploration.
I see. Okay.
Yeah, but our full result, our full result applies to sort of what you would think of as a more standard notion, with like you have this 1 over poly SAH factor. Though it doesn't technically apply to reward maximization.
I see.
Which is why we proved our sort of oracle impossibility result, which does.
The other question is that the cryptography, the conjecture that you've mentioned, it is a statistical conjecture, right? Like it's a statistical hardness conjecture, not a computational one.
It's computational.
Sorry, I don't. But it's saying that learning like parity under noise is conjectured to be inefficient, but that inefficiency is in terms of number of samples, no? Or it's in terms of computation?
It's in terms of computation. So like the sample complexity is actually going to scale polynomially with 1 over delta here.
Oh, okay.
And so we're actually considering a setting where, yeah, delta is super small, but we're interested in scaling super polynomially with delta inverse.
No, but I mean like the largely like this LPN question is that you're actually given enough samples so that if you had infinite computes, you could actually recover.
That's
like,
right. Yeah.
SK.
Yeah. If you have poly n and 1 over delta.
But the actual hardness is to say if you only have limited computational power, like you can't do it.
Yeah. Like if you only have like poly n and 1 over delta, for example, then we believe you cannot. If you only have that much computation.
I guess in this particular case, when we're talking about the complexity, you're essentially the whatever algorithm that tries to do this computation is basically given the access to generate any UI pairs as many UI pairs as it desires.
Yes, right? That's the cleanest way to formulate it.
Okay. Cool. I have some other like more not directly technical related comments, but maybe I'll let others ask first.
Sure.
If no one else has a question, maybe as well. I have a more general comment. So actually, I probably told Noah about this, but we had a open conjecture in one of our recent iClear papers on POM-DPs. So this is our policy evaluation in POM-DPs. I can send you later, but we have a conjecture of hardness. It's a purely statistical hardness, but I see a lot of maybe similarities or connections between the setting you're talking about, because it's also about having latent states, and things are simple and easy in the latent state, but you don't have access to that. Like instead, here you observe high dimensional context. There we have like only the sequence of observations, and we have a conjecture hardness of policy evaluation in a fairly general setting. And actually, partly I volunteered to host today's talk was because I actually had conjecture that maybe that hardness can be proved based on some kind of like cryptographical conjectures or something. Like I feel like there's some connection there. Like you maybe generate a secret key in the latest days, and ask the policies maybe try to decode it or something like that. Anyway, I just want to mention that because it seems like there's some similarity. If you're interested, like maybe you can take a look and then see if you have ideas for that.
Yeah, that sounds super interesting. I'll take a look. You said it's an iClear paper?
Yeah, I can send you email later.
Okay, cool.
Or put it over here. Yeah.
Got it. Thanks.
Should we stop recording?